175, and you don't have to do it this way. This is just for me is the easiest way. So these are my observed. Then I'm going to do my expected, and this is 250, 400, 150, and 200. And then I'm going to do my observed minus expected. So I'm going to get negative 50, 15, 25, and 10. And then I might as well do observed minus my expected squared. That's negative 50, right? Sorry. So I've got 2,500. Let's see, what 225, 625, 100, right? And then I might as, oops, that's my squared, by the way. And then I'm going to do my observed minus expected squared divided by expected. Okay? So 250, let's see, 2,500 divided by 250 is 10. I may have to do these guys right here. I've got set quit. I'm going to do 225 divided by 400 is 0.5625, 625, 625. Whoa, sorry you guys. 625 divided by 150 divided by 150 is equal to 4.17. And then 100 divided by 20 is 5. So I know that chi-squared is simply the sum of all these guys. All right, so what do let's see if I can do this thing in my head. How good am I? I got 19.6.7325, right? 19.7325. That looks about right. Oh, if not, we'll just fake it. 96, yeah, that's right. So wait, 19.7325, that's it. Okay, now, just like before, watch how simple this is. I'm going to go jump onto my chart. Now remember, my degrees of freedom in this case are, there are 4 categories, so it's 4 minus 1, which is 3. I'm going to pop out. Here's my chi-squared right here. Now watch how easy this is. Remember, we should probably pick an alpha level, but even though, watch how certain we can be. All right, first things first. If my degrees of freedom is 3, and I want my p-value to be 0.05. Now really think about that. What we're saying is if alpha equals 0.05, then my critical value for 3 degrees of freedom, just by looking at it, is 7.82. If alpha equals 0.01, then my critical value is equal to, what do we got, 11.35. Now remember how this guy works. I'm going to pop this open one more time. Ah, that's too bad. Remember how this works. The way that the chi-squared looks, the way chi-squared looks is it looks like that. So if I get far enough over, so if I pick alpha equals 0.05, then my critical value, let's see, what was it? What did that say again? 9 point something? 7.82. Then my critical value is 7.82. You know I'm going to have to change colors just because I love it so much. So this is my critical value. Well, in our case, my chi-squared was equal to, what was it, 19 point something? It was 19.7325. So chi-squared is 19.7325. Now we know that since chi-squared equals 19.7325 is in the critical region, we reject the null hypothesis. Whoa, but Ripley, wait a sec. You didn't mention what the null hypothesis is. Think about that. Let's write the null hypothesis just after having played with this. What do you think that the null hypothesis really is? What are we testing? Go back. We're testing to see if this distribution right here is close enough to this distribution. So what we're really testing, is whether or not, in our case, because we have 3 different deals, right? We're checking to see if the proportion in each one, not did I say 3? I meant 4, 4 different races or ethnicities. We're checking to see if they are all equal. Really? Now, you got to watch out for this equality here. In this case, I'm not really checking for equality, am I? I'm really checking to see if P1 is equal to 40% or 0.4. P2 is equal to, I forget what it was. Was it supposed to be 0.2? I forget. Let's look. It's 0.25, 0.4, 0.14, 0.15. So P1 is equal to, sorry about that, P1 is equal to I did it again, 0.25, 0.4. P3 is equal to 0.15, and then P4 is equal to 0.2. Now, traditionally, if we're looking for a uniform distribution, this is what we would write for our null hypothesis. However, we're starting to get pretty savvy, so I went ahead and jumped to the advanced move of checking to see if the distribution fits the claim. So that's another way that we could write up the null hypothesis if we wanted to. Now, there's a fancy way of writing the alternative. It's called at least one inequality, or ALOI, okay? Which means at least one of these values back here does not fit in the distribution. They could all miss. In fact, they all miss, don't they? But it appears as though, I would bet you that this guy right here, because it's a large proportion of what's supposed to be. Now this guy not so much, right? We're only off by 15 out of 400. That's not very big. That's what, 3.75%? This guy's off quite a bit too. This is 1 out of 7, right? So about 14% off. So those are probably the two that made it so that the data didn't fit the distribution. Okay? I don't know why I just stumbled over those words. All right? That's it. That's how it works. It's so easy. Basically, the general rule, and we're going to play with these in class, of course, is you're going to have observed, you're going to have expected, you're going to have it observed minus expected. It doesn't matter if you get the sign right on that because we square it, right? And then you're going to have an observed minus expected squared divided by expected. And then you just take the sum of them. If I take these guys, minus expected, and whoops, observed minus expected squared, that is equal to chi squared. And then all we have to do is take our degrees of freedom, and that equals k minus 1. And that's it. That's all there is to it. That's to check to see if a claimed distribution is actually descriptive of an observed distribution. Pardon me, too much caffeine again. All right, that's it. That's chi squared. We'll do some more in class. We'll putz around with it. Enjoy, man. This is your second to last lecture. We're going to jump into the next section here in just a minute. So enjoy and have a great day.